Hopefully you can hear me. Right, so this week we were, we went into group theory, things got very abstract. We talked yesterday about rotations in 2D, which hopefully at least not too difficult to visualize. Today we are actually going to take a trip back into 3 dimensions. So sort of rotations in 3D, okay? Right, how much can one say about these things? Well, sort of like with rotations in 2D, it shouldn't really surprise you that these things form a group, okay, for pretty much exactly the same reasons. And in fact, it is, this will actually form a Lie group. Right, so as we said yesterday, a Lie group is an infinite, it's a group of infinite size, but all the elements are actually related to each other through sort of, through continuous parameters, okay? And in the case of 3D, it shouldn't surprise you that there are actually 3 real parameters here, okay? And that will sort of drive a lot of the behavior. But, I mean, so this is actually fine for, sort of continuously related group elements, okay, which will be the rotations. But of course, you know that in 3 dimensions, you have another transformation, which is, of course, your spatial inversion. Okay, which takes you from, say, x, y, z to negative x, negative y, negative z. This sort of, in 3 dimensions, unlike in the 2-dimensional case, you cannot actually get you can't get this transformation from any of these guys. So this ends up being, sort of taking you into sort of another space of the group multiplication table. It's a little bit like when when we were drawing that multiplication table for the perturbation, for permutations, right? You had sort of you had your cyclic permutations occupying one quadrant of the multiplication table, and then on the other side, you had another part where you got, sort of to get to these sides, you would actually have a swap operation, right? Which is pretty much like your space inversion. Okay, similarly here. Okay, so much like that. Also, kind of like with the permutation group, this quadrant forms a subgroup. Okay, so if we talk about the group of rotations in 3D, we can think of this as isomorphic to, sort of that same discussion again yesterday, to the group of 3x3 orthogonal matrices. Okay, so here, again, right, we're the rotations, you can think of it in an abstract way. This would also be, basically this would be a matrix realization of those rotations, as well as the space inversion. And then the subgroup would be SO3. So this guy is with the determinant of the element being +1. Okay? So that keeps you just within the proper rotations. Okay, so that is the overall structure of these things. Let's see. Also talked a little bit about generators yesterday, right? So it shouldn't surprise you that given that we're talking about a Lie group, that there will be generators involved, and there are 3, not at all a surprise. You've actually seen this before. So we'll write down the exponential map as usual, which I'm sure that I've written down here somewhere. Somewhere around here. Well, anyway, okay. So you have the exponential map. So rotation tend to have an axis of rotation and then an angle. Okay. And this will be e to the minus I n. Let's see, wait. Got to have the angle in there, and then n dot j. Okay. We'll get to what these little bits are. Just want to check that. Okay. Again, as I said before, that sign, as well as the I, actually is a little bit of a convention. So, you know, if you look in other books, you do have to make sure that you're working with the right sign convention there. And then the generators, well, okay, so n is just a unit vector. Okay, giving you the axis of rotation. And then the generators are the familiar ones. You have J1, which is sort of rotation around, well, we'll sort of, you know, well, I'll just write it down in the first instance. So J1, 3 by 3 matrix. These guys, they are traceless. Matrices like that. Okay, so that's J1. J2 is, again, you know, the diagonal elements are 0. This guy is I and minus I here. And then J3, 0, minus I, 0, and then 0. Okay? So this is actually the that when writing down matrices, I've actually selected a basis. Okay, so in this case, the basis or the basis of the representation space are basically 3 vectors of that form. Okay, obviously, if we choose a different basis, you would have different forms of the generator. Okay, now, as I said, these should look really familiar to you from quantum mechanics. Now, at that time, they seemed, you know, mysteriously quantum mechanical, but it actually turns out that it's all coming from just geometry. So, the relationships between these generators is written in, well, yeah, written in this formula. Okay, so we'll actually talk about a Lie algebra. Okay, so the Lie group, of course, is the group of elements. The Lie algebra is actually the relationship between the generators. So in this case, we have J. Actually, I shouldn't use I because I'm going to use that for something else pretty soon. And yes, I could be lazy and use a kind of Einstein convention, but since I kind of gave you that whole thing about upper and lower indices, I'll just write the sum there. Okay. But again, you've seen this. You've seen this from quantum mechanics, and over there you called the generators the angular momentum operators. Now, because this is actually, you know, a relationship between the generators. And the generators are connected to the sort of basically, yeah, you might call it the local behavior. So if you have one element of the group, and then you want to find its neighborhood, find the behavior of its neighborhood, you use the generators. So the Lie algebra sort of determines what we call that local behavior. Okay, or, you know, relationships or between nearby elements. Okay, and just as a reminder, when we keep on talking about elements, we are actually talking about transformations. Okay? Doesn't give you everything, right? Because just like we said with SO2, remember there's, aside from the Lie algebra, there's also, and the local behavior, there is sort of at least one important global behavior that you have to worry about, which is the periodicity. And this is actually something which, now we have 3 parameters, so obviously you have the periodicity in the 3 parameters. There's kind of an interesting way to visualize that. So you can think in terms of, let's see, sort of a picture of SO3 group elements. Okay, excuse me. Now, as I said, you actually have 3 degrees of freedom. You have a unit vector, so that's 2 degrees of freedom, and then you have your your rotation angle. So let's just picture that. Picture what that space of parameters looks like. So the axis is just, we'll give that with, we'll say, have an angle theta. Well, so this is just the direction of the unit vector. So going from 0 to pi, okay, and let's say we'll give the azimuth 0 to 2 pi, okay. So that points in some direction. Let's see. All right, so you get your pointing off in some direction. That, okay, and then you have the amount of the rotation, okay, and that will actually be the length of this vector, okay, just in terms of visualizing the parameter space. And so we'll say the angle of rotation. Sorry, I changed the notation a little bit here. We'll call it psi. Now, this is where that periodicity enters, because if you rotate by, well, you know that if you rotate by 2 pi, you get back to the same rotation element. Okay. Actually, it's a little bit more restricted than that, because it actually turns out, at least in this way of visualizing the parameters, the psi would actually be sort of rotating around this axis, okay? But then the thing is that you can actually get, you can think, well, if you went out to just a rotation of pi, you can actually get the same rotation by having the axis point in the opposite direction and then rotate in the, by pi again, okay? So in fact, in this case, you actually have the length going from 0 to, the length of this vector will actually go from 0 to pi. And so the space of valid, of course, I drew this in the corner like that. The space of parameters for SO3 exists within this kind of solid sphere, but with the caveat that if you have a point on the sphere, on one end of the sphere, it's actually equivalent to an opposite point on the sphere. Okay? So this is actually, so from a topological perspective, the parameter space of SO3 is a little bit messy. Okay? Your interior of the sphere, you're fine. All your local neighbors, all the sort of neighboring transformations exist within a fairly small neighborhood, in parameter space. Okay, so you vary the parameter just a little bit, you get all the neighbors. But if you're actually sitting out here on the edge, at pi, then actually the neighborhood of that incorporates not just the neighborhood around here, but actually the neighborhood around here as well. Okay, so we won't go into huge details about all the problems that are associated with this, But if you ever happen to look in the literature, you will see this referred to as a double-connected, double-connected, I think the word was manifold. Okay. And yeah, it causes, obviously this kind of a thing causes a few problems because, you were hoping actually that most of your group behavior you were just going to be able to get from the local behavior. Okay. So clearly the local behavior is not going to be completely sufficient. Okay. Now, let's get back to the local behavior. Okay. And we're now going to take that other step. Jeez. And that is to talk about the representations. Okay. Now you remember in the case of SO2, we had these representations where there was one representation which was a trivial one. Okay. Everything mapped to the identity element. There was another one which was isomorphic to the rotations themselves. And then you had, other ones which would have sort of multiple values associated with the, sort of like 2-to-1 mappings and 3-to-1 mappings, so forth and so on. Okay. Same sort of thing here. It's actually a little bit more restrictive, and you have seen this algebra before, because it's all based upon this Lie algebra stuff. So let's just reach back into our familiar old quantum mechanics. Because as I said, it's not just quantum mechanics, it's actually geometry. So you have your total, your total J squared generator. And this thing actually commutes with all of the J1, J2, and J3. Okay, so J squared is equal to 0. Okay. So this is what we call the Casimir operator. In the case of SO3, there's only one Casimir operator. Some groups will actually have multiple Casimir operators. And then we will usually, we'll choose one as a special direction. So we'll sort of choose the third direction, or choose J3 as the sort of, as the sort of normative direction, I guess we'll call it. Okay, maybe I should just be a little bit more specific and not so mysterious about that. This is the one with the diagonal generator. Okay, and from there then we use the other ones to write down our raising and lowering operators, J1 plus or minus I, J2. Okay, this enables us then to, of course, write down what the various generators will be. And from that, again, pulling on from last year, you have J squared, and we'll write down the basis in a totally suggestive form, right? So J squared operating on J will give you that as an eigenvalue, okay? And J3 will simply give you M back. Okay? And then as for what the allowed values are, we have, these are what we call the finite dimensional representations. Okay? And so from that requirement, you will have that M is going to take values from minus J plus 1, et cetera, all the way up to plus J. J takes values from 0, also, of course, 1/2, 1, 3/2, 2, et cetera. Okay? And it's also worth just mentioning, because now this is actually going to label the representation. Okay? And for each one of these representations, you will then have a series of m values. So it's worth, just reminding ourselves the multiplicity of these is actually, of course, 1m value, 2m values, 3, 4, 5, etc. Okay, obviously that's of the it's 2j plus 1 is the multiplicity. Okay. Right. So we seem to have stepped from our sort of nice classical physics back into quantum mechanics. And if you're having nightmares about that, sorry about that. But then, it's worth asking, now that we're talking about this in this somewhat more general, context of group theory, what in the world are these representations? I mean, what are these representations? Okay. Okay? Or perhaps more specifically, what are the representation spaces? Because after all, we are still talking about rotations of things. The rotations are just the operations. What is actually being rotated is sort of the physical quantity. Okay? So let's see if we go into that a little bit. One thing to note is that very special one there with the multiplicity of 3, which of course in 3 dimensions should, make you think about something. There's, this is the representation. So j equals 1. That representation is the one which is isomorphic to 3D rotations. Okay, so so j equals 1 is the faithful representation, and shouldn't surprise you, it's the one with 3 degrees of freedom, because of course you had back here, you have 3 elements in the basis, and here you also have 3 elements in the basis. They're different, okay, different basis, but you still have the same number of degrees of freedom. On top of that, let's see, where am I in my notes? Right. These are, so an example of an example of this kind of representation space, actually, you do have, it doesn't have to be different, right? It can actually just be the Cartesian vectors, okay? So that's one thing. Another thing, actually, I should just show this picture to you because this is going to come up. The other thing is not just vectors, but also things like amplitudes, okay? Function distributions. So, for instance, spherical harmonics, okay? But in particular, it's not just all the spherical harmonics, it's the spherical harmonics with L equals 1. Okay, and you notice in this picture, that's these functions. Okay, this is labeled by sort of the 3m values, and you have the same. It's all the sort of same characteristics. Whether you're talking about vectors or spherical harmonics, you need a full 2 pi rotation to get back to the same thing. And the representation is isomorphic to full 3D rotations. So spherical harmonics are also just kind of convenient. And when you look at this picture, actually, it becomes pretty obvious that if you were to rotate these things around, around the main axis, that it does take the full 2 pi rotation. And then, you have the other spherical harmonics. So, with j equals 1, j equals 0. This guy is, of course, the trivial representation. So this would be scalar invariance. In other words, you rotate and they don't change. Or indeed, your L equals 0 spherical harmonic. And yeah, you look at the picture and yeah, it looks nice and spherically symmetric. Okay? No rotation necessary at all. Go to the higher representations, or the higher sort of spherical harmonics, and you look at this. This one, I mean, these guys, it's more obvious. I always have a little trouble figuring out this one, the m equals 0, 1. But in these cases, it's pretty obvious that if you rotate this by pi, right, by 180 degrees, you get back exactly the same thing. Okay? So this is much like, we talked about this with SO2 as well. Same sort of thing, this kind of, quantization of the rotation angle. But should add another thing to this, though. So here we have our, L equals 2 spherical harmonics. But where else did we see things that once you rotate them by 180 degrees, you get back to the same thing? Where did we see that? Okay, it has to be in the last 2 weeks, right? Okay. Sorry? No, that's going the other direction. Okay. No, this is actually right, sort of analogous to the vectors and scalar invariants, right? There was a particular tensor, in particular the rank 2 symmetric tensor. Okay. This guy actually, we looked at this in a little bit of detail, I think. Yeah. Wrote down components and tried rotating it. This thing also gets back to the original tensor after a rotation of just 180 degrees. Okay? So, so sometimes we will, in fact, talk about, in this case, rank 2 symmetric tensors as belonging to the J equals 2 representation of the rotation group. Okay, or, I'd be a little bit more specific. These rank 2 symmetric tensors are belonging to a J equals 2 representation space. Okay, because after all, these are the things being rotated. Now, it was just slightly more complicated than that, I should warn you, because if you remember from that derivation regarding the rotation of the rank 2 symmetric tensor, there was actually the trace of the tensor, which actually was invariant. Okay? So in fact, this guy has just a little bit more than J equals 2. It is in fact, and I'll get into what that direct sum means, it actually has a scalar invariant component as well as the J equals 2 bit. Okay? Right. Okay, any questions on representations? We'll sort of get into why this is important in the second part. Okay, just in case anyone was going to ask me what's the point of all this thing. Hopefully you'll get a sense of that in the next bit. Okay. Right, okay, so you can put your pens down for a few minutes. And again, because all this stuff has been horribly abstract, I, of course, want to go back and think about experiments. So I think, did I show these pictures? Yes? Yeah, I think I did, right. Yeah, so this is snow plus detector. This is in a big cavern, 2 kilometers underground. And, little people, big sphere, geodesic sphere with about nearly 10,000 photomultiplier tubes. It's a beautiful detector. Yeah, okay, now. Right, so I said that experimental physics is not like practical lab. You won't do this in practical lab, okay? It actually turns out that, because there's a fair amount of, just practical considerations in putting these things together. It turns out that, if you want to maintain or, service one of the PMTs, or, if actually, well, not just one PMT, but if you're actually doing an upgrade of every single PMT or photomultiplier tube in that sphere, it's kind of difficult to just have a ladder and reach them. So what tends to happen, or what's easier, is to, because the thing is going to fill up with liquid anyway, you might as well just, as you're filling it, put out a rubber boat and get people to, just kind of like boat their way up to the PMTs and do the various changes. So yeah, fortunately I did not have a picture of one of our graduate students doing this, but yeah, one of them was involved in that. This guy's a senior scientist in Portugal, so it's like we all sort of pitch in. And that's the PMT, that's the cavern wall. Okay. I am told, I have not been able to do this myself, a little bit unfortunate. I'm told it is actually a little bit more scary than this looks, because of course this is still 2 kilometers underground. It's really dark down there, but the water is very clear, and it's it does make people just get a little bit nervous. Now this is what the detector looks like when it is finally full. Okay, so there you see the PMTs out here. Now inside the PMT sphere, there's another thing which we call the acrylic vessel, and that's why, and it's the internal reflections. That's why you actually get this ring inside as well, and then you get a neck, because of course you have to be able to service what's actually inside. The point of, back in sort of 20 years ago, when people were doing the first neutrino experiments with this setup, it was ultra pure water outside, and then it was like heavy water inside. Okay, so we had to separate the volumes. Nowadays, well, in the most recent version of this experiment, we actually now have a lot of liquid scintillator in there. Okay, which is a completely different sort of beast. In the meantime, though, before we put the liquid scintillator in there, we did fill this up with water just to be able to sort of test things out. And I think that's what you're actually seeing. That's actually the water level right there. And yeah, you can actually see this is right above that neck. I can proudly say that I installed some of the PMTs in this top little bit. Very nervous when they give you this sort of 1,000-pound piece of equipment, or sort of, piece of equipment worth thousands of pounds, and they shoved it into your hands, and you say, "Are you sure you want to do that?" Most of my experimental work is actually playing with computers. So yeah, anyway, we did that, and yeah, sometimes people get to go down into the AV, which is also kind of one of those somewhat scary things. Right, okay, so this is a nice little picture. You can also see the ropes that actually hold the thing in place. And this is actually some data, which I think, oh, sorry, this actually comes from snow. So this is actually, more than 20 years old. You can actually see the date, 1999. And what this is, okay, so each one of these little dots is one of the PMTs firing. And I think in this case, giving a little indication of the time. Okay, so we can actually measure the times of these hits down to sort of about a couple nanosecond precision. And what this is you'll see this. I think you'll see this in the particle physics module, where a neutrino comes in, interacts with something, knocks out an electron. The electron's going faster than the speed of light in the medium, and therefore emits a lot of what we call Cherenkov radiation. It's sort of like a sonic boom, but in light. And because it only sort of goes about 10 centimeters, that cone of radiation just forms a nice little circle here, and it's quite a nice way of finding the direction of your neutrinos. And that way you can do things like point it back to the sun and do all sorts of really clever things with that. Okay? Right. So yeah, not relevant to B2, but just kind of fun. Perhaps more relevant to B4. Anyway, okay, so that's like one story of experimental physics. I can get into a few more later on. Yeah, so anyone think about any questions about what we've done so far? Any further questions? Okay, so right, we're going to talk about, in some sense, well, we're just going to delve into these representations a little bit. So yeah, you can pick up your pens again. Let's see, where am I in terms of the board? Right. Okay, now, the reason why we want to do this, or the reason why we sort of break things up into these representations, where did I write that? Yeah, so those rotations up there, okay, so labeled by different J values, is because by breaking things up that way, geez, which node? There I am. Yeah. Okay. By breaking things up like this, you can now write the state of a system in a, well, with a different basis. And, let's just take, for example, the case of the spherical harmonics. Okay, so if you were to do the sort of the j equals 1 spherical harmonics, so these guys, well, you can sort of write it out as 1, 1, 1, 0, 1, minus 1. Okay, so the state vector will look like, some sort of amplitude labeled by the L and the M. Okay, so 3 components, as you would expect, just like, for the faithful representation of SO3. For j equals 0, of course, you just get 1 amplitude. And for j equals 2, you get, 5 of them. So you can do sort of A22, A21, A20, 2 minus 2. Okay. Now, what happens if you actually have a system which is composed of several of these things? So it's actually not purely in one representation or another. Well, basically you just combine them in the same vector. So like in that case of the 0 plus 2, I would actually have a 0, 0 element, no 1 element, but then you would have all the 2 elements here. Okay, so you now have a 6-component matrix. And when you want to rotate this, the way that looks is that you have the rotation matrix for the 0, for the j equals 0, and then you have a 5 by 5 rotation matrix for the others. Okay, and then you just have zeros out here. Okay, so this is actually characteristic of what we would call, well, several concepts. So the construction here is actually what we call the direct sum. Okay, so yeah, and that's like, in that example, 0 plus 2. In terms of the state vector, the direct sum basically means you just put the amplitudes in the same column. But for the rotation matrix, it means that your rotation matrix now becomes block diagonal. Okay, so you actually have these nice zeros. And if you were to have direct sums of more complicated systems, you would have things like let's say you had your 0, 1, and 2, so you have a 3 by 3 block and a 5 by 5 block. Okay. Now the reason why this construction is kind of important is because if you look at that, if you look at this construction, you have something. You will find that you'll have something called invariant subspaces. Okay. And the definition of an invariant subspace is somewhere around here. Right. So let's say you had a vector space, you had a vector space U, and you had a subspace, vector space V and a subspace U, okay? Then you say, let's say for all elements G, okay, in that group, where G is a representation of some other group, okay? So minor little qualification there. Then, for all elements of U, then G operating on U will still be an element of U, okay? Or in other words, you can say that, with all these transformations, like rotations or whatever, elements of an invariant subspace will only transform into other elements of the invariant subspace. Okay, so it's kind of like, informally, you can say U is closed under G. Okay, if you like that language. Okay, and you see that from this construction because, yeah, you have these amplitudes, right? And when you actually do a rotation, any amplitudes that are associated with the J equals 2 representation only will change these amplitudes. They will not actually affect the J equals 0 amplitude. Okay, so now your rotation is broken up into these pieces that describe the rotation of things that rotate in the same way. Okay, now that, let's see, maybe I should write that down. Yeah, so let's see. So now what we find is that the rotations are sort of, well, it's sort of like factorized. Into, let's see, spaces that rotate in the same way. Okay, and what I mean by the same way, that is actually the global property. Okay, so now remember, when we actually derived the representations from the algebra, from the Lie algebra. Okay, so this enumeration of the representations actually just comes from the local behavior. But when you actually then, break it up into all these, in this case, finite dimensional representations, you find that these representations, yes, they are all describing rotations, but the things that actually differentiate one representation from another is that global property of the period, right? So J equals 1 has the period of 2 pi, J equals 2 has the period of pi, et cetera, et cetera. Okay? So in this sense, we sort of get back the fact that we still have these global properties, and that in fact determines what representation any object belongs to, or what representation space an object belongs to. So determines what representation space the object belongs to. Okay, and it's for this reason why we say, okay, right, vectors actually belong to the J equals 1 representation. Or another way of saying that is that vectors form a representation space of the J equals 1 representation. Whereas, let's say a traceless rank 2 symmetric tensor belongs to a representation space connected to the J equals 2 representation of the rotation group. Okay, so now you have both local and global properties together. Okay, now one final thing that I'd like to cover about that. Again, kind of related to the fact that you had this composite system back here. The composite system, of course, doesn't come about just from just from playing around with mathematical quantities. Sometimes you'll get it because, well, you just you have let's see, how should we describe this? Right, okay, so we have a composite system. So for instance, in a sort of, in physics, which is actually spherically symmetric, okay? So let's say, as one example, you took something that belonged to the L equals 1. I sometimes switch between L's and J's. Okay. I should really try to be consistent. So J equals 1, right, has, 3 amplitudes here. Okay. And it's going to interact with, somehow, something of the J equals 2 representation, something that actually belongs in a J equals 2 representation space. Okay? Now, it's still true that you have spherical symmetry. So these guys still have to, you might say, they still have to belong to a representation of some kind of the rotation group. And the question then is kind of which one it is. So, shall we say, let's see, the natural basis for describing this kind of a system, right, the interaction between these two things, is what we might call the direct product. So, yeah, we label the representations by the J value, and we form what we call a direct product. And what that looks like is a state vector where you essentially multiply all of the amplitudes of one by all of the amplitudes of the other. I guess I wish I did a, yeah, okay. 2, 1. I'm not going to write all of them down, okay? Just suffice to say, there are 15 elements here. Okay, 15 elements in this basis. Now, if you now try to rotate this, you've got quite a messy rotation matrix, because basically every element having been multiplied by every other element means that your rotation matrix is completely full. Okay, there are no nice 0 elements to simplify your life. But physicists are lazy. We like zeros. We like to simplify our life. So what we like to do instead is to decompose this. We say there exists a basis which separates that thing, the overall state, into invariant subspaces. Okay? And, here we know what the answer is because, of course, we took quantum mechanics last year. And what you find is that this is the decomposition. Okay? So the direct product of the L equals 1 and L equals 2 gives you a direct sum of 0, 1, and 2, which means that now, you just have sort of your A, 0, well, let's call them B now because it's a different basis, et cetera, et cetera. Of course, the size of this is 1 plus 3 plus, did I get that right? Sorry. Actually, these have to all be by the multiplicity. And something wait. I have actually written down something that must be slightly incorrect here. Okay, I'm going to have to actually, what did I do here? We had 3 times 5. Okay. You know what? I'm going to have to actually check my arithmetic because I actually, for some reason, I actually wrote this as 1 in my notes. It's 1 plus 2 plus 3. Wait, that is correct. Okay, sorry. Duh, yeah. This being the usual sort of quantum mechanical arithmetic, too. So, right, it's not this one. So because it's 1, that's a 3 by 3. Okay, 1, 0, minus 1. And then you have your 5, right? And then you have your 7. And of course, that gives you, when you write out all these components, your basis still has 15 elements. Okay? So yeah, finally, life makes sense again. And your rotation matrix will then take the corresponding form where you'll have a 3 by 3 rotation matrix, 5 by 5 rotation matrix, and a 7 by 7. Okay. Now, I think in the homework I have assigned a problem, or I have a problem where actually you can see how the rotation really works on spherical harmonics and how the generators give you a rotation matrix. So we won't go over that right here. Yeah, I think that is it for the regular rotations. Next week we're going to take a little look at that missing j equals 1/2 and see what that does for us. Okay? But otherwise, any questions? Okay, up there. Good question. When you say in what sense they are equal. Basically, that you should be able to take, they're equal in the sense that, that is the question, right? Equal, yeah. They're equal in the sense that you are actually trying to, that a state vector, which is described with this system, can be described in this basis. That's it. Okay? Right. So have a good weekend. See you next Wednesday.